In this capstone, you'll bring the full platform together. An LLM system that serves users, scales reliably, monitors for drift, and proves business value. The goal is not just a strong architecture, but a production strategy you can defend. Up to this point, we've moved from diagnosing a fragile LLM application to designing the platform around it. We addressed cost, latency, failures, GPU limits, and quality drift. Then we added optimized serving, reliability controls, observability, SLOs, and cost attribution. Now the capstone asks you to combine those pieces into one production-ready architecture proposal. This is where engineering decisions become something stakeholders could actually approve. Your proposal should trace the full production path from user request to processing, inference, response, and delivery. It should also explain reliability using the original failure modes as evidence for failover, recovery, and backup design. Add an operations plan for logging, monitoring, version control, quality checks, and drift detection. Then translate the redesign into business terms, with before and after metrics for cost, uptime, and expected return. A production LLM request is more than send prompt, get answer. It passes through controls that make the system safe, fast, and observable. The gateway authenticates and rate limits. Normalization puts the request into a consistent format, and policy checks enforce security and usage rules. Before inference, the semantic cache asks, have we already answered something equivalent? A hit returns quickly. A miss goes to the router, which selects the right model tier, provider, or fallback. Along the way, the platform emits traces, metrics, costs, prompt versions, and quality signals, so each response can be explained and operated. Reliability and cost control begin before the model ever runs. The gateway turns messy inbound traffic into a governed, traceable unit of work. It normalizes the prompt, tenant, user, and intent, then checks authentication, quotas, rate limits, and abuse signals. It also attaches the identifiers operations teams depend on: trace IDs, request IDs, prompt versions, priority, and budget class. Deadlines are assigned early, so overloaded systems can shed or reorder work deliberately. By the time inference begins, the platform knows who owns the request, how urgent it is, and how to account for it. Before optimizing model execution, ask whether the model needs to run at all. Many requests are repeats, near repeats, or simultaneous duplicates from different users. Exact, normalized, and semantic cache keys catch those cases at different levels of risk. Deduplication handles live spikes by sending one request to inference while equivalent callers wait for the same result. The guardrails are tenant and version boundaries, so cached answers do not cross customers or stale model releases. Measure caching like a product feature: hit rate, tokens avoided, latency saved, and dollars saved. A mature LLM platform treats model choice as a business decision, not a default setting. Simple, frequent, low-risk requests should go to efficient, fine-tuned models served through VLLM, keeping latency and unit cost under control. Complex, sensitive, or low-confidence requests can escalate to a stronger premium model. Then build in resilience. If the primary path times out, degrades, or misses an SLO, trigger a fallback response or alternate model. Every routing decision should be logged with its version, reason, confidence, and cost impact. Self-hosting only saves money when GPUs stay busy without becoming unstable. VLLM helps by continuously batching requests and managing the KV cache efficiently, so more tokens move through the same hardware. Quantization can improve efficiency further, but only where quality remains acceptable. The key mental model is workload isolation. Small models, large models, premium tenants, experiments, and latency-sensitive traffic should not all compete in one pool. Autoscale from real operating signals: GPU utilization, queue depth, tokens per second, out-of-memory events, and P95 or P99 latency. Efficiency comes from controlled saturation, not simply adding GPUs. In a reliability review, every control should have a failure story. Semantic caching is not only a speed feature, it absorbs repeated requests so downstream inference capacity is not wasted. Circuit breakers watch timeouts, error rates, and latency, then stop traffic from flowing to a degraded model, provider, or GPU pool before failure spreads. Retry budgets and deadlines keep recovery attempts bounded, so retries do not become the outage. Load shedding and priority queues decide what must survive under overload, protecting critical user flows while non-essential work waits or drops. Resilient systems assume the first path will sometimes fail. The important step is making the next path explicit. Start with a retry, but only if it fits the latency budget. Then move to an alternate local pool, an external provider, a cached answer, or a safe failure message. Each step still needs validation, schema, policy, risk, and task-specific rules. And degradation should never be silent. Tag the response and emit events like deadline exceeded or fallback triggered. That visibility helps teams tune reliability while giving users a predictable experience, even when the ideal path is unavailable. Observability has to be built into every hop, not added after launch. Each request should carry OpenTelemetry trace context from the gateway through cache, routing, inference, fallback, validation, and cost attribution. That creates one end-to-end story when latency spikes or an answer fails. Metrics show system health: latency, errors, cache hits, routing mix, token usage, and GPU condition. Structured logs explain decisions, including prompt version, model version, tenant, route, and fallback reason. Cost events connect technical behavior to spend, showing tokens, provider, model tier, GPU time, and cache savings. In production, telemetry only matters when it drives decisions. Start with user-facing SLOs: availability, P95 latency, timeout rate, and successful responses. Then add platform signals that explain why those SLOs move, such as cache hit rate, queue wait, GPU out of memory, fallback rate, and routing errors. Alerts should focus on impact and urgency: error budget burn, provider degradation, drift, cost spikes, and quality regression. Finally, separate dashboards by audience. Executives need risk and trend. Product needs user impact. Platform teams need causes. On-call needs action. Reliability is not just uptime. It also means knowing which version produced which behavior and catching quality movement early. Every prompt, model, router policy, and data source should be versioned, so regressions can be traced to specific changes. Production traffic is sampled and checked with golden datasets, human review, automated evaluations, validators, and user feedback. Drift may appear as new input patterns, weaker retrieval context, changed output style, rising refusals, or falling eval scores. When alerts fire, the system should support rollback, rerouting, reevaluation, or fine-tuning into the next controlled version. The 62% ROI story has to be more than "we changed the architecture." It should show where money was leaking before: repeated external API calls, inefficient routing, retries, timeouts, and uncontrolled token growth. Then connect each design choice to a measurable saving. Semantic caching avoids paying twice for similar work. Deduplication and routing reduce unnecessary calls. Self-hosting, quantization, and batching lower unit cost. The strongest narrative is cost per successful request. Spend drops, reliability improves, latency falls, and gross margin expands while operational risk goes down. Bringing an LLM platform into production is an integration challenge, not a single optimization. Your proposal should connect architecture choices to reliability, quality, and cost outcomes. Make the trade-offs explicit. Defend ROI with mechanisms like caching, routing, batching, and attribution. Then validate the design with telemetry. From here, adapt the capstone to your workload. Build the roadmap, measure, iterate, and operationalize.